We will now complete our survey of the graphs of the 6 basic trigonometric functions by examining the graphs of tangent and cotangent functions in 2.4. But first, let's focus on graphing tangent. Tangent presents an interesting graph, but like secant and cosecant, it does contain some asymptotes. So let's look at the relationship between tangent, as obtained from the unit circle, and the graph of tangent in the coordinate plane. Recall that from the unit circle, tangent of an angle alpha is calculated as the ratio of the y-coordinate to the x-coordinate. So let's make the observation first that when the angle, the input, is 0, tangent of 0 radians is 0. Y equal to 0 divided by x equal to 1 yields a ratio of 0. So we could probably be really specific here and say tangent of 0 radians yields the ratio of 0. Now, working from the middle up to the top here, we're going to allow the angle x to increase from 0 radians to pi over 2 radians. So as x, the angle, approaches pi over 2, we can observe the pattern of the values of tangent. First of all, notice that at pi over 4, where the x and y coordinates are the same on the unit circle, tangent of pi over 4 has a value of 1. So tangent increases as the angle increases from 0 to pi over 4, tangent increases from 0 to 1. As we continue rotating towards pi over 2, as the angle increases from pi over 4 to pi over 2, the value of tangent also increases. But as soon as we approach or reach pi over 4, then this ratio y divided by x becomes undefined. 1 divided by 0 is undefined. We know that tangent is undefined at pi over 2. For that reason, we're going to have a vertical asymptote on the graph at pi over 2. However, we can make an observation about the pattern of values as the angle approaches pi over 2. As the denominator decreases, notice as the angle rotates towards pi over 2, the x value is decreasing while the y value is increasing up to 1. As the denominator decreases and the numerator increases, then the value of tangent actually approaches infinity. We are treading on the grounds here of a concept called a limit, which you'll ultimately learn in calculus. But it's good to begin thinking about these patterns as you increase your mathematical rigor. Now, let's do the same thing. Rotating from x equals 0 to negative pi over 2. So as the angle changes from 0 to negative pi over 2, so the argument here is approaching negative pi over 2, then tangent begins at 0, it approaches negative 1, and then once again reaches this value, this undefined value, negative 1 over 0. So as the denominator decreases down to 0 and the numerator approaches negative 1, the value of tangent of x, we say, approaches negative infinity. This indicates that on the graph, as the x-coordinate gets closer and closer to the vertical asymptote at negative pi over 2, where tangent is undefined, then the y values will be following that asymptote, heading towards negative infinity. All right, let's go ahead and translate this analysis onto the graph. Now, completing our t-chart here, or our xy ordered pair chart to graph the function tangent of x, we've already discussed that tangent of negative pi over 2 and tangent of pi over 2 are both undefined. This means that on the graph, we're going to have a vertical asymptote at x equals negative pi over 2 and x equals pi over 2. I'm going to go ahead and label those vertical lines with their official equation. Now, as we observed on the unit circle, tangent of negative pi over 4 is negative 1, tangent of 0 is 0, and tangent of pi over 4 is 1. So here's a list of 3 key points, or 3 ordered pairs, that we can plot to determine the pattern of tangent. So when x is negative pi over 4, y is negative 1, Let me go ahead and label my scale here on the y-axis, -1, -2. I'll do 1 unit per tick mark. So at -pi/4, tangent has a value of -1. It passes through the origin 0, 0, and at pi/4, tangent has a value of 1. Now, as we observed up here, as the angle gets closer to pi/2, the value of tangent explodes up to infinity. And as the angle approaches -pi/2, the value of tangent decreases down to -infinity. Consistent with the behavior of any function near an asymptote, this curve is approaching the asymptote but not touching or crossing it. What we see here is one fundamental cycle of tangent. Observe that it achieves all of its possible values between these two asymptotes, where we see a distance of pi. So where the period of sine and cosine is 2 pi, the period of tangent is pi. This means that that fundamental cycle will repeat every pi units. So just like we saw a distance of pi units between the first two asymptotes, we can anticipate that there will be a distance of pi units between the next two asymptotes. So if we take pi/2 and we add pi to it, we're going to end up with 3 pi/2. So the next asymptote would occur at 3 pi/2. Similarly, we'll see one over here on the left side at -3 pi/2. In between the asymptotes, tangent is going to follow a similar pattern as that first fundamental cycle. It almost looks like a cubic polynomial where you have an increasing function sort of snaking its way there through the middle. So here we have a wider snapshot of the graph of tangent, but keep in mind that this fundamental cycle repeats an infinite number of times across the x-axis. With this guide in mind, we can now recognize the location of every possible asymptote on the graph of tangent. If we start with the first one, pi/2, we know that the next one is going to come pi units later. And then after that, there will be another asymptote pi units later, so on and so forth. So one way that we can express the location of all of the asymptotes is to say they occur at x equals the first asymptote pi/2 plus a multiple of pi later. So k times pi, where k is an element of the integers, represents the distance to the next asymptote. Also note that maybe a shorter, more efficient way to express the location of these asymptotes is to observe that we're looking at odd multiples of pi/2. So another possible way to express the asymptotes would be to say x equals 2k plus 1 times pi/2. Remember, if k is an integer, as we've specified here, then 2k is an even integer, and an even integer plus 1 is an odd integer. So the way that I can express in general odd integers is with the expression 2k plus 1. So at odd multiples of pi/2, we have an asymptote. Once we've done the hard work to locate the asymptotes, then we're going to specify that the domain is defined everywhere except those asymptotes. So in set builder notation, we can say the domain is the set of all x such that x is not equal to, and I'm going to use the 2k plus 1 pi/2 expression. You can use either of the expressions that we wrote on the asymptote line, but we do have to specify that k is an element of the integers, or you can write out in words k is an integer. So we express the domain in set builder notation because to do it in interval notation would require an infinite number of intervals, right? And so set builder notation is very efficient. Now notice the range for tangent is anything from -infinity to infinity. So where sine and cosine both have a finite range, secant and cosecant has sort of a broken range that comes in two intervals. The range of tangent is -infinity to infinity. Now, once you know this new parent function, then all of the same transformations that we've been studying apply similarly to tangent. So let's practice graphing tangent with some transformations. So on example 2 here, we're looking at the graph of tangent of pi/2 times x. Notice the argument has been multiplied by a constant. When the argument is multiplied by a constant, this generates a change in the period of the function. Recall that when this happened for sine or cosine or secant or cosecant for that matter, we took the original period of the function, which was 2 pi for sine, for example, and we divided by that constant. We're going to do the same thing here, except we have to recognize that the original period of tangent is pi, and we're going to divide not 2 pi, but pi by this coefficient pi over 2 that lives right here. That is a complex fraction. So to simplify the complex fraction, we can multiply by the reciprocal of the denominator, and we end up very simply with a period of 2 units. So the period of this function is 2 units. So our basic fundamental cycle will occur in a distance of 2 units. Now, just like the original function is split over the y-axis, this one will also be split over the y-axis. Instead of reaching to negative pi over 2 and pi over 2 for the asymptotes, this one is going to reach to negative 1 and 1. So I am going to change the scale on my x-axis here. I'm just going to rewrite it in integer form. So for every 2 units on the x-axis, I'll set that to be an integer value of 1. We'll do this in both the positive and negative directions. Then the first asymptote will occur at x equals negative 1, and the second one at x equals 1. So I'm going to go ahead and label the equations of those asymptotes, x equals negative 1 and x equals 1. Now, if x is equal to 0, tangent of 0 is 0. So this tangent curve is going to cross both axes at the origin. Now, if x is equal to, let's say, 1/2, pi over 2 times 1/2 is pi over 4, and tangent of pi over 4 is 1. So when x is equal to 1/2, tangent is equal to 1. So again, we're going to see the same pattern with this transformed function that we saw in the original parent function. The difference is the scale, of course, on the x-axis. So here's one fundamental cycle of tangent, but we need to graph 2 cycles. So I'm going to repeat this shape. I'm going to translate it to the right. Notice the distance between asymptotes is the value of the period 2 units. So the distance between the next 2 asymptotes will also be a period of 2 units. This means that the next asymptote occurs at 3. And in between those asymptotes, tangent achieves that same fundamental shape. So there are 2 periods or 2 cycles of this new transformed tangent function. Now, let's go ahead and give the location of the asymptotes in general and state the domain and range. Observing that the asymptotes are occurring at odd integers, we could say the asymptotes have equation x equals 2k plus 1. Remember, that is our general way of expressing an odd integer. X equals 2k plus 1. And I guess I don't need parentheses here. I can take those off and specify that k must be an element of the integers. This is a necessary component of the expression of the asymptotes. Of course, you don't have to write it in code. You can write k is an integer in words, but it's necessary because if k is not an integer, let's say k is equal to a fraction like 1/2, then that would not generate a location of the asymptotes. Now remember, once you have the location of the asymptotes, the domain is defined as everywhere except where those asymptotes occur. So x cannot be equal to 2k plus 1 for k in the integers. So the domain is everywhere else. Now the range is the same as the range as the original function. That is negative infinity to infinity. Let's go ahead and practice the graph of another transformed tangent function. This one will have a change in the period, and it will also have a horizontal shift. Like we did with sine and cosine, it'll be really important to express the argument in factored form. That is, if x has a coefficient, it is necessary to factor it out of the argument. Now, it's still in the argument, but it's factored out of this parenthetical element. Dividing both of those terms by 2, we end up with x plus pi over 2. So now we can see that there's a horizontal shift indicated by this constant, and there's a change in the period indicated by this constant. To calculate the new period, I'm going to take the original period of tangent, which is not 2 pi but pi, and I'm going to divide by that coefficient 2. So we have a period of pi over 2. This means that the distance between the asymptotes will be pi over 2. Now, because this one does have a horizontal shift, we're going to use an inequality analysis technique like we did with sine and cosine to figure out exactly where that first fundamental cycle is going to occur. So remember, the original tangent function achieves one fundamental cycle for x, the argument, between negative pi over 2 and pi over 2. I'm going to apply that concept to this new function. So we know that one fundamental cycle will occur where the argument is between negative pi over 2, our argument is 2 times x plus pi over 2, and pi over 2. Notice the strict inequalities here, not inclusive with the equals. Strict because we have an asymptote at those two locations. So this tangent function should achieve one fundamental cycle for the argument ranging between negative pi over 2 and pi over 2. Now, let's solve for x. If I divide all three parts of this inequality by 2, I'm going to end up with negative pi over 4 less than x plus pi over 2. And now you can think of dividing by 2 the same thing as multiplying by a half, if that makes it a little bit easier. Then we're going to add pi over 2 to all three parts of this inequality. Oh, I'm sorry, I spoke wrong. Subtract pi over 2 from all three parts of this inequality. So to trap x in the middle, we'll subtract pi over 2 from all three parts. So we need to add negative pi over 2 to negative pi over 4. I would need a common denominator of 4 there. So notice if we multiply this by 2, we're going to have to multiply this by 2. So we can add negative pi over 4 to negative 2 pi over 4, and we're going to end up with negative 3 pi over 4. Okay, now if you just sort of ignore the pi's for a minute, negative 1/4 plus negative 1/2 is negative 3/4, and then you can attach a pi there. Positive 1/4 minus 1/2 over here on the right side is negative 1/4 or negative pi over 4. Now, just in case I lost you there, let me show you exactly what I'm doing. For the left side, we were evaluating negative pi over 4 minus pi over 2. So I'm going to rewrite that with a common denominator. That's negative pi over 4 plus, there we go, minus 2 pi over 4 to get negative 3 pi over 4. Okay? And similarly for this operation on the right side, getting a common denominator, we'd have pi over 4 minus pi over 2, or pi over 4 minus 2 pi over 4, which gives me negative pi over 4. So what does this mean? This means that one fundamental cycle of our transformed tangent will occur between negative 3 pi over 4 and negative pi over 4. So I'm going to locate negative 3 pi over 4 on the graph and construct a vertical asymptote there. So this vertical line has equation x equals negative 3 pi over 4. The next vertical asymptote occurs at negative pi over 4, so that's located right here. I'm going to label its equation down below, x equals negative pi over 4. Tangent is going to cross the x-axis at the midpoint between those two vertical asymptotes. Then, halfway between that point and the asymptote to the right, tangent will have a value of negative 1. Halfway between that point and the asymptote to the left, tangent will have a value of negative 1. Then tangent will snake its way through the center, following the nature of the tangent function. Now we want to graph two cycles of this function, so let's make some observations about these first two asymptotes. Notice if I calculated the distance between these two asymptotes by finding their difference, I'd have negative pi over 4 minus negative 3 pi over 4. That's the same thing as negative pi over 4 plus 3 pi over 4. That gives me 2 pi over 4, which reduces to pi over 2. That should not be a surprise because remember the period of our function is pi over 2. So the distance between two asymptotes is equal to the period, pi over 2. So if I want to find the location of the next asymptote, I need to add pi over 2 to this last asymptote here, negative pi over 4. When we do that, we're going to obtain positive pi over 4. So this asymptote has equation x equals pi over 4. In between those two asymptotes, tangent is going to exhibit the same behavior that it did in that first fundamental cycle. Try that again. I think I can do a better job. There we go. And we have the graph of two fundamental cycles of this transformed function. Now let's do the hard part and see if we can express the location of every possible asymptote on this graph. Now it's easier than it looks. I'm going to start with the first positive asymptote, which occurs at pi over 4. And I know that the next asymptote is going to come at a multiple of the period pi over 2 units later. So we can say pi over 4 plus k pi over 2, where k is an element of the integers. Then, once we know that, we can say the domain is the set of all x such that x does not equal those locations. At those locations, tangent is undefined. Elsewhere, tangent is defined. The range for this tangent function then is negative infinity to infinity. Now before you go, I do want to show you how to check this on your calculator. So let's take a peek at the graph on our calculator. We're going to go to y. First of all, let me start with the mode. Make sure that you are in radian mode to graph this function. If you're in degree mode, you're going to get something that doesn't look like what we did. So make sure that you are in radian mode. I'm going to clear out what I have here. I'm going to type in my my new function, tangent of 2x plus pi. Now, I'm going to do the zoom trig, to see a picture of the graph. Now, the calculator yields more than 2 fundamental cycles. Also recall that in zoom trig mode, the unit on the x-axis is pi over 2. So I can see by observing on the x-axis that tangent crosses at multiples of pi over 2, and we can see that's what happened on our graph by hand. This means that one fundamental cycle occurs between x equals negative pi over 4 and pi over 4. But if I want to be absolutely sure and I want the calculator graph to match the graph that I did by hand, I can manually set the window. So I'm going to type my window button and set the x minimum to match the leftmost asymptote that we came up with. That was negative 3 pi over 4. Then I'm going to set the rightmost value to match the rightmost asymptote that we came up with. That was pi over 4. Also, to match the graph that we did by hand, we can use an x scale of pi over 4. There's no need to change the y min and y max, but what I should see on the graph then is an exact match of the graph that we did by hand. So make sure you explore your calculator. It's a great way to check those graphs. The bottom line of this particular section is you have a new parent function, tangent of x. Make sure you know the basics of one fundamental cycle of tangent, and that you know how to manipulate all of the transformations for tangent.